Scientists have confirmed 6,000 planets beyond our solar system, 6,000 worlds, and the one most similar to Earth, the closest confirmed twin humanity has ever found, sits 239 trillion miles away. 239 trillion. We will visit that world. We will see what lives there, what threatens it, and what stands between us and it forever. We will meet the planets closer than you think, and far more dangerous than you expect. If you enjoy the journey, subscribe, so we do this every week. Ready? Let's go. Somewhere out in the dark, there is a world almost exactly like ours. Scientists have been searching for it for decades. They have pointed telescopes at hundreds of thousands of stars, sifted through mountains of data, and confirmed the existence of more than 6,000 planets orbiting other stars. 6,000 worlds. And after all of that searching, after all of that effort, the closest confirmed match to Earth sits so far away that every number we use to describe the distance stops making sense. That world is called Trappist 1e. And before this is over, you will understand exactly why finding it changed everything, and why reaching it may be impossible forever. But first, we need to understand the scale of what we are actually dealing with. Because most people hear 6,000 exoplanets confirmed and picture something like a catalogue, a list, a menu of options humanity could eventually visit. The reality is completely different. The reality is that 6,000 planets have been confirmed, and not a single one sits anywhere close to us. The closest rocky candidate in a habitable zone is still so far away that Voyager 1, the fastest travelling spacecraft humanity has ever launched, would need hundreds of thousands of years to reach it. So how did we end up here? How did we find 6,000 worlds and still feel completely alone? It started in 1992. That year, astronomers confirmed the very first planet ever found orbiting another star. It was orbiting a pulsar, a dead spinning star that blasts radiation in all directions, so the planet was almost certainly a scorched wasteland. Still, the confirmation shook the scientific world. Other stars had planets. The universe was not empty after all. Then, in 2009, NASA launched the Kepler Space Telescope. Kepler's job was simple in theory, and staggering in practice. It stared at a patch of sky containing about 150,000 stars and watched for tiny dips in starlight. When a planet passes in front of its star, it blocks a tiny fraction of the light. Kepler caught those dips. Thousands of them. Over the following years, it confirmed hundreds of planets, then thousands. Scientists started sorting them by size, temperature, and type. And then the question shifted. Finding planets was no longer the hard part. The hard part was finding the right one. Scientists needed a way to rank planets by how Earth-like they actually were. So they built a scoring system. They called it the Earth Similarity Index. It runs from 0.00, meaning completely alien, to 1.00, meaning identical to Earth. Earth scores exactly 1.00. The index measures 4 things: radius, density, how fast a planet holds onto objects on its surface, and surface temperature. Any planet scoring above 0.80 is considered a serious candidate. As of right now, more than 6,000 planets have been confirmed. Over 8,000 additional candidates are still waiting for verification. That is more than 14,000 worlds in the running. And after measuring all of them against this scale, the highest confirmed score belongs to a single planet, 40 light-years away. 40 light-years sounds like a manageable number. It sounds like a distance with a destination at the end of it. That feeling will not last. Because the moment you start converting light-years into something human, the number becomes almost too large to say out loud, and the planet that sits at the end of that distance carries a secret that scientists are still arguing about right now. What that secret is, and why it changes everything about the search for life, comes next. The Earth Similarity Index sounds simple. It is anything but. When scientists say a planet scores 0.95 on the index, most people picture something like a report card, a grade, a rough estimate. In reality, The index is built from 4 specific measurements, and each one tells a completely different story about whether life could survive on that world. The first measurement is radius. A planet with roughly the same radius as Earth tends to have a similar gravity at its surface. Too small, and the planet cannot hold on to an atmosphere. Too large, and the air becomes so thick and heavy that the pressure on the surface would crush most life forms we know of. Earth's radius sits at about 3,958 miles from its centre to its surface. Planets that stay within about 20% of that number stay in the running. The second measurement is density. Density tells scientists what a planet is made of on the inside. A planet with Earth-like density is almost certainly rocky. It has an iron core, a silicate mantle, and a crust you could stand on. A planet with much lower density is probably a gas giant or a water world, and the rules change completely in those environments. The third measurement is escape velocity, which is a fancy way of asking how hard gravity holds things down. On Earth, you need to reach a speed of about 7 miles per second to leave the planet's gravity entirely. A planet with similar escape velocity tends to hold onto the right mix of gases in its atmosphere. Too weak, and the atmosphere leaks away into space over millions of years. Too strong, and a thick blanket of gas traps heat until the surface becomes an oven. The fourth measurement is surface temperature. Life as we know it needs liquid water. Liquid water only exists within a specific temperature range. Too cold, and it freezes. Too hot, and it boils away. The ideal surface temperature for an Earth-like world sits somewhere between roughly -13 and 104 degrees Fahrenheit. Now here is where it gets complicated. The Earth Similarity Index measures physical similarity. A high score tells you the planet is built like Earth. It says almost nothing about whether life actually exists there. A world could score 0.95 and still be completely dead, locked in permanent radiation, stripped of its atmosphere, or frozen on one side and boiling on the other. And that distinction matters enormously. Because out of all the confirmed planets in the database right now, the one with the highest Earth Similarity Index score carries several serious question marks alongside its impressive number. Scientists also require a second condition before taking any planet seriously as a life candidate. The planet must sit inside what astronomers call the habitable zone. This is the region around a star where temperatures are right for liquid water to pool on a rocky surface. Too close to the star, and the water evaporates. Too far away, and it freezes solid. The habitable zone is sometimes called the Goldilocks zone because the distance has to be just right. The third condition is the most basic. The planet must be rocky. Gas giants and ice giants follow completely different rules. Only a rocky terrestrial world with solid ground gives life the kind of stable surface it needs to get started. As of right now, only one confirmed planet checks all 3 boxes with a score above 0.90. And the planet that scores 0.95 has a feature so strange, so extreme, that half its surface may never see daylight at all. What that feature is, and what it means for anything trying to survive there, is something you're about to find out. Trappist 1 E-scores 0.95 on the Earth Similarity Index. That number is the highest ever confirmed for any verified exoplanet. To understand what it means in real terms, start with the measurements. Trappist. 1E has about 91% of Earth's radius. Its mass is about 77% of Earth's. Its density is almost exactly Earth's. The gravity on its surface is about 93% of what you feel standing on the ground right now. A person weighing 150 pounds on Earth would weigh about 140 pounds there. The world is smaller, a little lighter, but built almost identically to ours. It orbits a star. It sits inside that star's habitable zone. And it is rocky. All 3 boxes checked. For those reasons, scientists consider it the most Earth-like confirmed planet ever found. But confirmed is the key word, because there is an unconfirmed candidate sitting in a database right now with a score of 0.98, practically identical to Earth in radius, mass and temperature. That candidate has never been verified by a second telescope or a second method. It could be real. It could be a measurement error. The scientific community has not settled the question, so that score stays in the theory column for now. Unknown. Trappist. 1e, by contrast, has been studied by multiple telescopes and confirmed through multiple detection methods. Its numbers are solid. Its position in the habitable zone is confirmed. The James Webb Space Telescope pointed directly at it in September 2025 and produced the first atmospheric data ever gathered from this world. Scientists used the telescope's spectrograph, an instrument that reads light like a fingerprint to identify chemicals, to analyse starlight filtered through the planet's edge during 4 separate transits. The team ruled out a thick hydrogen and helium atmosphere. Beyond that, the results got complicated. Some researchers reported a faint chemical signal that could suggest a thinner, more complex atmosphere. Others concluded the signal was almost certainly coming from the star itself rather than from the planet. No conclusion has been confirmed. Theory. So as of right now, Trappist 1e might have an atmosphere, or it might be a bare rock floating silently in space. Here is the part that should pull your attention. Even if this world has an atmosphere, even if it has oceans, even if it has everything life needs, we have no way to reach it with any technology that exists today or is planned for the near future. And the reason for that comes down to one single number: 40.7 light years. That is the confirmed distance between Earth and the TRAPPIST-1 system. Say it fast and it sounds almost modest. Say it slow and start converting it, and the floor drops out from under you. 1 light year is the distance light covers in 1 full year, travelling at about 186,000 miles per second. That works out to about 5.879 trillion miles per light year. Multiply that by 40.7. The answer is approximately 239 trillion miles. 239 trillion miles. That is the gap between us and the most Earth-like world ever confirmed. And 239 trillion miles, it turns out, is just the beginning of the problem. The Trappist. One system does not look anything like our solar system. In our solar system, the 4 rocky inner planets spread out over hundreds of millions of miles. Mercury orbits about 36 million miles from our star. Venus orbits about 67 million miles out. Earth sits at about 93 million miles. Mars stretches to about 142 million miles. Those 4 planets together span a ring of space that is enormous by human standards. The entire TRAPPIST-1 system, all 7 planets, fits comfortably inside the orbit of the innermost planet in our solar system. Every single world in that system orbits closer to its star than Mercury does to ours. 7 planets packed into a space smaller than Mercury's orbit, each one roughly Earth-sized and rocky. That image is worth sitting with. 7 worlds, all crammed into an area of space that our own solar system considers its inner parking lot. The star they orbit is tiny. TRAPPIST-1 is an ultra-cool red dwarf, and it's only slightly larger than Jupiter. Our star, by comparison, is about 10 times wider than TRAPPIST-1. If our star were the size of a basketball, TRAPPIST-1 would be closer to a golf ball, so dim and so small that for most of human history, no one even knew it existed. It was only identified as a star of interest in the 1990s. The Trappist telescope in Chile, a small robotic instrument pointed at the sky night after night, caught the first hints of planets crossing in front of it. Scientists saw the star dim slightly, then recover, then dim again in a regular pattern. That pattern meant planets. In February 2017, the full announcement came. 7 Earth-sized rocky worlds, 3 of them sitting inside the star's habitable zone. The scientific community reacted with something close to shock. Finding 1 Earth-sized world in a habitable zone was rare. Finding 3 in the same system, around the same star, all at once was extraordinary. Of those 3, TRAPPIST-1e stood out immediately. Its size, density, and estimated temperature placed it closest to Earth of any world in the system. Scientists began referring to it as the crown jewel of the Trappist-1 group. But the tight, compact nature of this system also raised immediate red flags. Planets that orbit so close to a star get bombarded with radiation. They interact gravitationally with each other in ways that can destabilize orbits over long time scales, and they almost certainly end up tidally locked, which is a feature of this system so important that it gets its own chapter. For now, hold this picture in your mind. 7 rocky worlds packed into a space the size of Mercury's orbit, circling a star barely bigger than a planet, 40.7 light-years from Earth, a system unlike anything in our own neighbourhood. And somewhere inside that compact alien arrangement, a world about the size of ours sits waiting. The problem is not finding it. We found it. The problem is that the distance between us and it is so large that the numbers humanity uses every day completely break down trying to describe it. And the breakdown starts the moment you try to picture what 239 trillion miles actually means. That breakdown is what comes next, and it is going to feel stranger the further in you go. 239 trillion miles. That number does not mean anything on its own. Numbers that large almost never do, so build it slowly, piece by piece, until the size of the gap becomes impossible to ignore. Start with something familiar. The distance from New York City to Los Angeles is about 2,800 miles, a cross-country road trip, a long flight, a distance that feels real because people actually travel it. Now go further. The distance from Earth to the Moon is about 239,000 miles. That trip took the Apollo astronauts about 3 days. 3 days of travel to cover 239,000 miles. That number happens to match the first 3 digits of the distance to Trappist-1e, which is 239 trillion miles. So Trappist-1e is 1 billion times farther away than the Moon. Not a little farther, 1 billion times farther. Now try the distance from Earth to our own star, which is about 93 million miles. The fastest spacecraft humanity has ever built, the Parker Solar Probe, can reach speeds close to 430,000 miles per hour in its closest approaches. Even at that speed, reaching our star would take about 9 days. Trappist. 1e sits about 2.6 million times farther from us than our star does. Now try converting the full distance into a car trip. If you got in a car and drove at 60 miles per hour toward Trappist-1e, never stopping for gas, food or sleep, the trip would take approximately 455 quadrillion years. 1 quadrillion is 1,000 trillion. 455 quadrillion years is roughly 30 million times longer than the current age of the universe. The universe is about 13.8 billion years old. Your road trip would outlast it by 30 million times over. These comparisons are confirmed math, not estimates. Confirmed. And yet 40.7 light-years is considered nearby in cosmic terms. The Milky Way galaxy stretches roughly 100,000 light-years from edge to edge. The nearest large galaxy to ours, Andromeda, sits about 2.5 million light-years away. Trappist-1e is practically in our backyard by those standards. The problem is that our backyard is still incomprehensibly large by any human measure. Here is the comparison that tends to hit the hardest. The light you see coming from Trappist-1e through a telescope right now left that star 40.7 years ago. You're watching that world as it looked in the mid-1980s. Whatever is happening there right now, you will not see it for another 40 years. Send a message at light speed asking if anyone is home, and the earliest you could possibly receive a reply is 81 years from now. That gap, that silence, that delay is the reality of the distance. And if the distance alone feels impossible, what comes next will make it worse. Because the spacecraft question has an answer. Scientists have calculated exactly how long it would take to send something there using the fastest machine humanity has ever launched, and the number will stay with you. Voyager 1 is the farthest human-made object ever sent into space. NASA launched it in 1977. Since then, it has been moving away from Earth continuously, every second of every day for nearly 50 years. It carries a golden record with sounds and images from Earth, a message in a bottle aimed at the stars. It crossed into interstellar space, the region beyond our solar system's outermost boundary, in 2012. No other object built by human hands has ever travelled as far. Right now, Voyager 1 moves at roughly 38,000 miles per hour. That is fast by any standard we use on Earth. 38,000 miles per hour is about 49 times the speed of sound. A commercial airplane cruises at around 500 miles per hour. Voyager 1 travels at roughly 76 times that speed, and at 38,000 miles per hour, it would take Voyager 1 approximately 685,000 years to reach the Trappist 1 system. Confirmed. 685,000 years. For context, modern humans, people with language, tools, art and social structure, have existed for roughly 300,000 years. If Voyager 1 had launched at the very moment modern humans first appeared on Earth, it would still have hundreds of thousands of years left to travel before reaching Trappist 1e today. NASA's New Horizons probe, which flew past Pluto in 2015 and is now heading deeper into space, travels at roughly 35,000 miles per hour. At that speed, reaching Trappist 1 would take about 817,000 years. The Apollo Command Module re-entered Earth's atmosphere at about 25,000 miles per hour. That was the fastest a crewed vehicle has ever travelled. At Apollo re-entry speed, the journey to Trappist 1e would take over 1 million years. So what would it take to get there in a human lifetime? To reach Trappist 1e in, say, 100 years, a spacecraft would need to travel at about 24 trillion miles per year. That works out to roughly 2.7 billion miles per hour. The fastest speed anything has ever been measured travelling is the speed of light, at about 670 million miles per hour. Getting to Trappist 1e in one human lifetime would require moving at 4 times the speed of light. Special relativity, one of the most tested and confirmed theories in all of science, says that is physically impossible for any object with mass. Confirmed. Every road, every spacecraft, every imaginable engine closes this gap by almost nothing. And yet there are people working on a real proposal. A plan involving lasers, tiny probes the size of a coin, and speeds that make Voyager 1 look like it is parked. That proposal has a name, it has funding, and it has a travel time to the nearest star that is actually within the range of a human lifetime, though Trappist 1e would still require centuries. But before getting to that plan, there is something even more immediate to look at. A planet much closer than Trappist 1e. A planet in a habitable zone just 4 light years away. A world that sounds, on paper, like the answer to everything. It is not. And why it is not is one of the most important stories in modern astronomy. 4.22 light years away, there is a planet in a habitable zone. 4.22 light years is close, by the standards of interstellar space. Proxima Centauri is the closest individual star to our own, and the planet orbiting inside its habitable zone was confirmed in 2016 by the European Southern Observatory. Scientists named it Proxima Centauri b. Its minimum mass is about 1.055 times Earth's. It sits at the right distance from its star for liquid water to theoretically exist on its surface. On paper, it sounds like the discovery of the century. In practice, it is potentially one of the most hostile surfaces in the known galaxy. The problem is Proxima Centauri itself. Proxima Centauri is a red dwarf star, and red dwarfs are magnetically violent in a way that larger Karma stars are not. They produce eruptions of energy called superflares, which are massive bursts of radiation and charged particles that blast outward from the star's surface. Proxima Centauri fires these superflares at least 5 times per year. Confirmed, 5 times per year the star detonates, and the planet in its habitable zone sits extremely close, about 4% of the distance between Earth and our own star. It absorbs each of those blasts directly, with almost no buffer between itself and the source. scientists studied a specific flare that erupted from Proxima Centauri in 2016, just weeks after the planet's discovery was announced. That single flare made the star 1,000 times brighter in ultraviolet light in the span of just 10 seconds. Confirmed. In a decade of observation afterward, scientists confirmed that Proxima Centauri regularly fires flares of extreme intensity. A 2019 monitoring campaign, running for 40 straight hours, caught one extreme flare that boosted the star's ultraviolet output by 14,000 times its normal level. The effect of those flares on a planet like Proxima Centauri b would be severe. Computer models show that flares at this frequency and intensity would strip 90% of an Earth-like ozone layer from the planet within 5 years. Confirmed. The ozone layer is the shield that blocks ultraviolet radiation from reaching a planet's surface. Without it, ultraviolet light hits the ground at roughly 100 times the lethal dose for the most radiation-resistant organisms ever tested on Earth. Over longer timescales, billions of years of this bombardment would likely eliminate any protective atmosphere entirely, leaving the surface exposed and bare. Some scientists argue that if Proxima Centauri b has a deep global ocean, life might survive in the water beneath the surface, shielded by liquid depth from the radiation above. That remains a theory. Theory. The surface itself, as understood today, looks like a very difficult place for life to begin or last. And beyond the radiation, Proxima Centauri b faces another major problem. A feature it shares with Trappist 1e, a feature that makes survival on these close-orbiting worlds far more complicated than distance alone. That feature involves what happens when a planet orbits its star so closely that the star's gravity permanently locks one face of the world in place. And what it creates is stranger than almost anything else in this story. When a planet orbits close enough to its star, gravity stops letting it spin freely. On Earth, the planet rotates once every 24 hours. That spin gives us day and night, morning and evening, a cycle that drives weather, ocean currents, and the rhythms of nearly every living thing. Earth's rotation is one of the basic facts of life here. Trappist. 1e does not rotate that way. Scientists confirmed it is tidally locked to its star. Confirmed. That means one hemisphere of the planet permanently faces the star, bathed in constant daylight forever. The other hemisphere permanently faces away, locked in endless darkness and cold. The planet orbits, but it always shows the same face to the star. The moon does the same thing with Earth, which is why we always see the same side of the moon from the ground. For the moon, tidal locking is an interesting quirk. For a planet trying to support life, it creates a split world. The day side of Trappist 1e receives constant radiation from its star, concentrated on one hemisphere without relief. Temperatures there could climb high enough to make liquid water unstable. The night side, permanently cut off from any starlight, could drop to temperatures where gases freeze and fall out of the air as snow. The two halves of the planet exist in completely different temperature regimes, separated not by seasons but by a permanent, unmovable boundary. The only zone that might sit at survivable temperatures is a thin ring between the two extremes. Scientists call it the terminator zone, the line where daylight ends and permanent night begins. Along that ring, temperatures could theoretically be stable enough for liquid water and survivable conditions. The terminator zone on Trappist 1e would be a thin band, lit by a sun that sits permanently low on the horizon, like an eternal sunset stretched all the way around the planet. Whether that zone could actually support life depends almost entirely on one unknown variable: atmosphere. If Trappist 1e has a thick enough atmosphere, wind systems could carry heat from the scorching day side around the planet and deliver it to the frozen night side. That circulation could stabilize temperatures across a much wider region, possibly even making parts of the night side survivable. Some models show that under the right atmospheric conditions, liquid water could exist across a significant portion of the planet's surface, not just at the terminator ring. But as of right now, scientists do not know whether Trappist 1e has a meaningful atmosphere at all. Unknown. The James Webb Space Telescope's first observations ruled out a thick hydrogen-rich atmosphere. Beyond that, the data is unclear. There may be a thinner secondary atmosphere, or there may be nothing at all above the rock, and without an atmosphere to move heat around, the picture gets bleak quickly. The day side bakes, the night side freezes, and the Terminator Strip, the only potentially livable zone, becomes a narrow ring stretched around a tidally locked world, 40 light-years from anyone who could answer the question. Trappist 1e raises the question. Proxima Centauri b raises almost the same one. Both planets orbit in habitable zones. Both are probably tidally locked. Both have the same unknown hanging over them, and both orbit red dwarf stars, which creates a problem far bigger than either planet individually. Red dwarf stars are the most common stars in the Milky Way. Roughly 70 to 75% of all stars in our galaxy are red dwarfs. They are small, dim, and cool compared to our own star. Most of them are invisible to the naked eye, despite being far closer to Earth than many of the bright stars you can see at night. Proxima Centauri, the closest star to our solar system, is a red dwarf, Trappist. 1 is a red dwarf. Barnard's star, the second closest individual star to Earth, is a red dwarf. Because red dwarfs are so common, any rocky planet in a habitable zone is statistically far more likely to orbit a red dwarf than any other type of star. That sounds like good news for finding life in the galaxy. In one crucial way, it is exactly the opposite. Red dwarfs have a serious magnetic problem. Compared to larger, more stable stars, red dwarfs are extraordinarily active in their early lives, and some remain active for billions of years. They generate powerful magnetic fields that erupt regularly as flares and coronal mass ejections, which are violent eruptions of magnetized plasma thrown outward from the star's surface. These eruptions can strip hydrogen from a planet's upper atmosphere over time, slowly peeling away the protective gas layer that makes life possible. But the deeper problem is geometry. Because red dwarfs are dim and cool, their habitable zones sit extremely close to the star. Trappist. 1e orbits at about 2.9% of the distance between Earth and our star. That puts the planet close enough that it ends up tidally locked, as described already, and close enough to receive repeated radiation bombardment from every flare the star produces. A study of Proxima Centauri over a 40-hour observation window in 2019 caught one extreme flare that made the star 14,000 times brighter in ultraviolet light. Confirmed. At that level of ultraviolet output, reaching the surface of any nearby planet, any surface unprotected by a thick ozone shield, would reach 100 times the lethal threshold for the most radiation-resistant bacteria found on Earth. Scientists who study red dwarf habitability note clearly that the question is unresolved. Theory. Some models show that a planet with a strong magnetic field and a thick atmosphere could survive the bombardment. Others suggest that over billions of years, the combined effect of tidal locking, radiation, and atmospheric stripping would leave any planet in the habitable zone of a red dwarf as a bare, airless rock. The tension in this debate shapes everything scientists currently think about where life might exist in the galaxy. If red dwarf planets cannot support life, the number of potentially inhabited worlds drops dramatically. If they can, the galaxy may be far more crowded with life than anyone assumed. The answer changes everything about our place in the universe. And while scientists argue about red dwarfs, there is a planet orbiting a completely different kind of star. A calmer, more familiar star that once held the title of Earth's closest twin. A world that was announced with enormous fanfare, given a nickname that captured the imagination of millions, and then quietly demoted when the numbers came in. That world has its own kind of problem, and its problem is distance on a scale that makes Trappist 1e look close. In July 2015, NASA held a press conference. The announcement drew international attention. A team using the Kepler Space Telescope had found a planet orbiting a sun-like star, at roughly the same distance from that star as Earth orbits ours. The planet had a year lasting 385 days, just 20 days longer than an Earth year. The star it orbited was the same type as ours, a yellow, stable, middle-aged star, and it was 6 billion years old. NASA's science chief called it the closest thing to a second Earth ever found. The planet's name was Kepler 452b. The press called it Earth 2.0. By the Earth Similarity Index standards, it scored reasonably well. Its star type matched. Its orbital period matched. The energy it received from its star was similar to what Earth receives, and unlike Trappist 1e and Proxima Centauri b, it was orbiting a calm, stable star that did not regularly bombard it with violent radiation. Then the size numbers came in. Kepler 452b is about 60% wider than Earth in diameter. Its mass is estimated at roughly 5 times Earth's mass. That much mass creates a gravitational pull at the surface about twice as strong as what we feel here. A person weighing 150 pounds on Earth would weigh about 300 pounds there. The leg muscles required to simply walk upright would be enormous. Climbing stairs would feel like carrying another full human being on your back every step. Scientists classify worlds at this mass range as super-Earths. They are rocky, but the conditions at the surface are dramatically different from our own planet. The atmosphere, shaped by higher gravity, would be thicker and more pressurized. Volcanic activity might be more intense. The physics of the world would feel alien to anything that evolved under Earth conditions. And then there is the distance. Kepler 452b sits 1,400 light-years from Earth. Confirmed. Convert that using the same math applied earlier. 1 light-year is about 5.879 trillion miles, multiplied by 1,400. The result is roughly 8,230 trillion miles. At Voyager, one speed of 38,000 miles per hour, reaching Kepler 452b would take approximately 24 million years. Confirmed. 24 million years ago, on Earth, the continents looked slightly different, and the ancestors of modern apes were first diverging from other primates. The human species did not yet exist. The entire human story, from the first stone tools to space telescopes, fits inside a fraction of the travel time required to reach what was once called Earth 2.0. Trappist. 1e, at 40 light-years, is 34 times closer than Kepler 452b, and even Trappist 1e takes 685,000 years at Voyager speed. So the calmer star, the more familiar orbit, the planet that sounds the most like home, turns out to be the most unreachable of the candidates discussed so far. And there is still one more planet to consider, a candidate with the highest Earth Similarity Index score ever recorded, confirmed by no one, orbiting a star that nobody has yet looked at closely enough. Its score is 0.98. Its location is over 1,000 light-years away, and it might not even be real. There is a planet in a database with an Earth Similarity Index of 0.98. That score is higher than Trappist 1e's 0.95. It is higher than any confirmed planet ever found. On paper, this world is more like Earth than any other candidate in the entire catalogue of known exoplanets. Its designation is KOI 4878.01. The name is awkward, so think of it simply as the candidate. It orbits a G-type star, a yellow star like our own. Its estimated mass is approximately 0.99 times Earth's mass. Its radius is about 1.04 to 1.05 times Earth's radius. Its estimated surface temperature sits within a few degrees of Earth's average. It completes one orbit around its star every 449 Earth days, close enough to an Earth-length year that the difference is barely noticeable. In almost every measurable way, this candidate looks like a copy of Earth, and scientists cannot confirm it exists. The data behind this candidate comes from the Kepler Space Telescope. Kepler detected a signal that looked like a planet transiting its star, and the measurements from that signal produced the extraordinary similarity scores. But a transit detection alone is not enough to confirm a planet. Astronomers require at least one independent method, usually radial velocity measurements that detect the gravitational wobble a planet causes in its star, to verify that the signal is a real planet and not an instrument artifact, a background star, or some other false positive. The candidate has never been verified by a second method. It remains unconfirmed. Unknown. That matters enormously. Kepler's detection catalogue contains thousands of confirmed planets, but it also contains false positives, signals that looked like planets, but turned out to be something else. Without independent confirmation, the candidate with the highest Earth similarity index ever measured sits in a kind of scientific limbo. Scientists cannot say it is definitely there. They cannot say it is definitely not there. The data exists. The score exists. The planet itself remains a question, and even if it were confirmed tomorrow, the distance is brutal. The candidate orbits a star roughly 1,075 to 1,135 light-years from Earth. At Voyager 1 speed, reaching it would take approximately 18 to 20 million years. Confirmed, based on distance and speed calculations. So the closest confirmed Earth-like world is 40 light-years away and may have no atmosphere. The most Earth-like confirmed world is the same one. The best unconfirmed candidate is over 1,000 light-years away and may not even exist. And the closest habitable zone planet of any kind is 4 light-years away and sits inside a radiation storm. Every option on the table carries a different version of the same problem. The distance is always the ceiling. But there is a world even closer than Proxima Centauri b that was confirmed just recently, sitting only 6 light-years away. Scientists announced it in 2024. It is the second closest known exoplanet to Earth. The discovery made headlines, and then scientists looked more closely at what they had actually found. 6 light-years away, there is a planet that is close. By the standards of interstellar travel and astronomical searching, 6 light-years is practically next door. Barnard's star, the star this planet orbits, is the closest individual star to Earth after the Proxima Centauri system. Astronomers have been watching Barnard's star for over a century. It moves across the sky faster than any other known star from Earth's perspective, sliding noticeably against the background of distant stars over just a human lifetime. Scientists announced the confirmed discovery of a planet orbiting it in October 2024. They named it Barnard's star B, the second closest exoplanet ever confirmed to Earth. The announcement landed in science publications worldwide. Then the details came out. Barnard's star B has a mass of roughly 0.3 Earths, less than 1/3 of Earth's mass. It orbits its star every 3.15 Earth days. That means a full year on this world lasts about 3 days, and it sits extremely close to its star, about 20 times closer than Mercury sits to our own star. Its surface temperature hovers around 125 degrees Celsius, which is 257 degrees Fahrenheit. That is hotter than boiling water at sea level. Confirmed. So at 6 light-years away, the second closest known exoplanet is a scorching, airless rock, roughly 1/3 the size of Earth, completing a full orbit in less time than a long weekend. The Earth Similarity Index score for a world like this sits near the bottom of the scale, and yet the discovery still matters, not because Barnard's star B is a twin of Earth, but because of what it proves about the galaxy. Scientists now have confirmed exoplanets at 4.22 light-years, 6 light-years, and 40 light-years. Every star they look at closely enough seems to have something orbiting it. The closest stars, Proxima Centauri and Barnard's star, both have confirmed planets. The Trappist 1 system, 40 light-years away, has 7. Statistical models built from thousands of confirmed detections suggest that Earth-sized planets in habitable zones likely exist around at least 1 in every 3 stars in the Milky Way. There are about 400 billion stars in our galaxy. The math suggests something like 130 billion potentially Earth-like worlds, theory based on statistical modelling. If that estimate is even close to accurate, there should be Earth-like planets within 10 or 20 light-years of Earth that we simply cannot detect yet because they do not transit their stars from our line of sight. The universe may be full of Earth twins. They may be scattered through every neighbourhood of the galaxy, waiting to be found by telescopes that do not exist yet. But as of right now, we cannot see them. We cannot confirm them, and the ones we can confirm are separated from us by distances that break every unit of measurement we use. And the one closest thing to a confirmed twin, the one world scientists keep coming back to, the planet at 0.95 with a habitable zone orbit and roughly Earth-like gravity, got its first close look from humanity's most powerful space telescope just a few months ago. What that telescope found, and what it still could not answer, changes the stakes entirely. In September 2025, the James Webb Space Telescope pointed at Trappist 1e. The James Webb Space Telescope is the most powerful observatory humanity has ever launched into space. Its primary mirror stretches about 21 feet across, made of 18 hexagonal gold-coated segments that unfold like a flower after launch. It sits about 1 million miles from Earth, orbiting a gravitational balance point in space, where it stays cool enough to detect infrared light from objects billions of light-years away. Scientists designed a specific observation plan for Trappist 1e. The goal was to look for an atmosphere. When a planet passes in front of its star, a small fraction of the starlight filters through the planet's atmosphere, if one exists, before reaching the telescope. Different chemicals in the atmosphere absorb different colours of light, leaving gaps in the spectrum that work like chemical fingerprints. By analysing those gaps across multiple transits, scientists can identify what gases might be present above the planet's surface. The team conducted 4 transits of Trappist 1e through the telescope's near-infrared spectrograph instrument. They analysed the data over several months. The first clear result was a ruling out: Trappist. 1e does not have a thick primary atmosphere composed mainly of hydrogen and helium. Confirmed. That kind of atmosphere is what a planet retains directly from the cloud of gas it formed inside. The absence of it tells scientists that if any atmosphere exists, it is a secondary one, built later through volcanic outgassing or other geologic processes. Beyond that, the results became uncertain immediately. Some members of the research team reported a faint chemical signal in the data that might suggest a methane signature. On Earth, methane in the atmosphere is produced largely by biological processes, living organisms releasing gas as a byproduct of metabolism. A methane signal on an exoplanet would be an extraordinary hint, the kind of signal that would send every telescope on Earth pointing in the same direction. But other scientists on the same team cautioned strongly against that interpretation. The signal, they argued, was most likely coming from the star itself rather than from the planet's atmosphere, a known complication called stellar contamination, where the star's own chemical fingerprint bleeds into the planetary measurement. Theory. No definitive conclusion was possible from 4 transits. NASA's Pandora mission, a smaller telescope designed specifically to monitor stars continuously before, during and after planetary transits, was planned for launch in 2026. Its purpose is to separate stellar contamination from genuine planetary signals by building a detailed model of each star's behaviour. With Pandora's data, scientists expect to get a much cleaner read on what, if anything, exists above the surface of Trappist 1e. As of right now, the world at 0.95 may have an atmosphere capable of supporting life. It may be a bare rock. Both possibilities remain open. Unknown, and the telescope that could answer the question is either preparing to launch or already in operation depending on when you're listening to this. Meanwhile, a proposal exists to actually send something to the nearer stars. Not a full spacecraft. Something much smaller. Something that moves at a speed that makes Voyager 1 look completely stationary. And the plan to build it is already funded. In 2016, physicist Stephen Hawking and billionaire Yuri Milner stood together and announced a plan to reach another star. The project is called Breakthrough Starshot. The initial investment was $100 million. The concept is unlike anything previously attempted in space exploration. Rather than building a large spacecraft with engines and fuel, Breakthrough Starshot proposed building something closer to a postage stamp. The idea works like this. Engineers would manufacture tiny probes, sometimes called nanoprobes or light sails, that weigh about 1 gram each, roughly the weight of a paperclip. Each probe would carry a miniaturized camera, communication systems, and other instruments. Attached to each probe would be an extremely thin sail made of a lightweight reflective material. On the ground, an array of powerful lasers would focus their combined energy onto the sail at the moment of launch. The pressure of laser light pushing on the sail would accelerate the nanoprobe to a significant fraction of the speed of light. The proposed target speed is between 15 and 20% of light speed. At 20% of the speed of light, the probe would be moving at about 134 million miles per hour. To understand what that speed looks like, consider this. The distance from Earth to the Moon is about 239,000 miles. At 20% of light speed, a probe would cross that entire distance in approximately 6 seconds. Confirmed based on calculation. At that velocity, reaching the Alpha Centauri system, which includes Proxima Centauri and Proxima Centauri b, would take between 20 and 30 years. After arriving, the probe would send data back to Earth at light speed, with the signal taking about 4 years to arrive. The entire round trip for information would span roughly 25 to 35 years, a timescale a human lifetime could contain. The Trappist-1 system sits roughly 10 times farther than Proxima Centauri. At the same 20% light speed, reaching Trappist-1e would take approximately 200 to 270 years one way, still within the range of a long-term civilization project, though no single person would see the results. But Breakthrough Starshot remains theoretical as of now. Theory. The laser array required to accelerate a probe to these speeds would need to be hundreds of times more powerful than anything currently built. The engineering challenge of focusing that energy precisely on a 1 gram sail without burning it up is unsolved. The probe would need to survive interstellar space, where microscopic particles hit at relativistic speeds with enough energy to punch through thin materials. And perhaps most critically, there is no proposed method for slowing the probe down once it arrives. At 20% light speed, it would fly through the Trappist-1 system in a matter of hours, snapping what images it could before disappearing into the dark on the other side. The proposal is real. The funding is real. The engineering solutions are not yet. And even if Breakthrough Starshot works perfectly, the probe that arrived at Trappist-1e would be the size of a postage stamp, travelling alone, with no way to stop, no way to return, and no way to carry any human being along for the ride. The gap remains, the distance remains, and the question of whether we could ever actually close it physically, with a vessel large enough to matter, runs directly into the hardest wall in all of physics. Special relativity does not care about ambition. Albert Einstein published the theory in 1905, and in the more than 100 years since, every test ever designed to challenge it has confirmed it instead. Confirmed. One of its core results is this: no object with mass can reach or exceed the speed of light. The faster an object moves, the more energy it requires to accelerate further. As it approaches light speed, the energy required approaches infinity. There is no engine, no fuel, no trick that gets around it. Light speed is about 670 million miles per hour. Even at a fraction of that speed, the engineering challenges are beyond anything humanity has ever attempted. Voyager 1, after nearly 50 years of travel, moves at 38,000 miles per hour. Getting a meaningful payload, something large enough to carry instruments, power systems, and communication equipment, to even 1% of light speed, which is about 6.7 million miles per hour, would require energy roughly equivalent to the entire annual electricity output of the United States. based on current propulsion physics. Getting to 10 or 20% would require vastly more. And then there is the problem of what space actually contains. Interstellar space feels empty. It is not. Between the stars, there are particles. Hydrogen atoms, dust grains and other microscopic matter float through the void at low densities. At low speeds, these particles are irrelevant. At relativistic speeds, the fraction of light speed, each hydrogen atom becomes a high-energy projectile. A spacecraft moving at 20% light speed would hit those particles with enough force to generate radiation and erode the spacecraft's material over time. Engineers would need to design shields capable of absorbing that punishment across decades of travel. Then there is the communication problem. At 40 light-years away, any signal sent from a probe at Trappist 1e, travelling back to Earth at light speed, would take 40 years to arrive. The scientists who designed the mission might be retired or gone before the first image came back. Some researchers have proposed ideas that sidestep the speed limit, concepts involving space-time manipulation or exotic forms of matter that theoretical physics allows on paper. Warp drives, wormholes, shortcuts through the geometry of space. All of these remain entirely in the theoretical column. Theory. No experiment has ever detected the exotic matter required. No laboratory has ever bent space-time in a controlled way. These ideas are mathematically interesting and physically unproven, so the honest picture is this. Getting a meaningful spacecraft to Trappist 1e, one large enough to do real science or carry life, is beyond any foreseeable engineering horizon. Breakthrough Starshot's nanoprobes represent the only credible near-term proposal, and even those face unsolved technical walls and a 200-year travel time, the fastest thing in the universe is light, and light itself takes 40.7 years, one direction. That is the hard ceiling above every plan humanity has ever made for reaching Trappist 1e. And yet, right now, telescopes are gathering data on that world. Missions are being planned. Scientists are working on refining every detail of what Trappist 1e actually is, even if they cannot get there. And what those scientists have learned about the star it orbits adds a completely new layer to the problem of survival on that world. Because the red dwarf at the centre of the Trappist 1 system has a behaviour pattern that no planet sitting that close can fully escape. Trappist 1 is not a calm star. It is an ultra-cool red dwarf, which sounds mild. In terms of surface temperature and total energy output, it is genuinely the cooler, quieter end of the stellar spectrum. Its surface temperature is roughly 4,900 degrees Fahrenheit, compared to about 10,000 degrees Fahrenheit for our own star. It burns dimmer, slower, and longer than almost any other type of star in the galaxy. But magnetically, red dwarfs can be brutal. Trappist 1 is no exception. In 2017, shortly after the 7-planet system was announced, a team of scientists studying archival data found evidence of a significant flare from Trappist 1 that had occurred during earlier observations. The flare was estimated to be powerful enough to deliver a damaging dose of ultraviolet radiation to any planet sitting within the system's habitable zone. That finding triggered a wave of follow-up studies. Researchers modelled what happens to an Earth-like planet in the Trappist 1 habitable zone over millions of years of exposure to repeated stellar activity. The results were sobering. Ultraviolet radiation at the levels produced during flares could break down ozone in a secondary atmosphere over time, progressively weakening the planet's radiation shield. Trappist 1e's orbital distance from its star is about 2.9% of the distance between Earth and our star. The planet is inside the habitable zone, meaning temperatures are theoretically right for liquid water. But that close orbital distance also means the planet absorbs each flare with very little attenuation. The distance buffer that protects Earth from the worst of our star's outbursts is almost absent at Trappist 1e's position. Scientists studying the system note that Trappist 1 appears relatively quiet for a red dwarf, especially given its age. The star is estimated to be between 5.4 and 9.8 billion years old, significantly older than our own star's 4.6 billion years. Older red dwarfs tend to be less magnetically active than younger ones, which is actually a point in Trappist 1's favour. Theory, but quiet for a red dwarf still means something quite different from the calm stability our own star provides. One study examining Trappist 1's magnetic environment concluded that the innermost planets in the system, including Trappist 1e, likely experience a space weather environment far more energetic than what Earth faces. The planet's best protection against all of that radiation would be a magnetic field of its own. Earth has one, generated by the churning of molten iron in its core, and it deflects a significant portion of the charged particles thrown at us by our star. Whether Trappist 1e has a meaningful magnetic field is unknown. Statistical. Unknown. If tidal locking has slowed or stopped the planet's interior rotation, the dynamo process that generates planetary magnetic fields may have weakened or shut down entirely. A planet without a magnetic field, orbiting a flaring red dwarf at close range, would be a world where the sky itself becomes hazardous. And that brings everything back to the original question. Whether life could survive there at all, the answer is genuinely unknown. Scientists with strong arguments sit on both sides of the debate. But before examining what survival on Trappist 1e might actually look like, it helps to step back and consider what the distribution of all these planets, confirmed and unconfirmed, tells us about the universe as a whole. Because the numbers carry a message that goes far beyond any single world. NASA has confirmed 6,007 worlds orbiting other stars, 6,007. Each one detected, measured and verified through at least one rigorous scientific method. Some were found by watching a star dim as a planet crossed in front of it. Some were found by measuring the tiny gravitational wobble a planet causes in its star's motion. Some were found directly as faint dots of light next to much brighter stars captured in long exposure images from space telescopes. And alongside those confirmed planets, scientists have identified more than 8,000 additional candidates still awaiting verification. That puts the total number of known and suspected worlds at over 14,000. 14,000 planets beyond our solar system, confirmed or being checked, all discovered within the last few decades. For most of human history, astronomers had no idea whether any other stars had planets at all. The philosophical debate went back centuries. Some thinkers believed the universe was full of worlds. Others argued Earth was singular and unique. Before 1992, no confirmed evidence existed either way. The first confirmed exoplanet, orbiting a pulsar, settled the philosophical debate permanently. Stars have planets. The universe is not empty. What the last 3 decades of exoplanet science have revealed goes far beyond that initial confirmation. Statistical analysis of the data suggests that nearly every star in the Milky Way has at least one planet orbiting it. Some stars have multiple. The Trappist 1 system, with 7 confirmed rocky planets around a single small star, is considered an extreme case, but the overall pattern holds. Planets are not rare, they are the default outcome of how stars form. The more specific question is how common Earth-like planets in habitable zones are. The Kepler mission, which operated for 9 years and monitored about 150,000 stars, gave scientists enough data to run serious population estimates. Current estimates suggest that somewhere between 7 and 20% of Sun-like stars host a rocky planet in the habitable zone. Theory based on statistical modelling. If even the conservative end of that estimate is correct, there should be billions of potentially Earth-like worlds in the Milky Way alone. The nearest one, statistically, ought to exist within 20 light-years of Earth. But detecting Earth-sized planets at that range requires them to transit their star from our line of sight, a geometrically unlikely alignment for most stars. Current telescope technology misses planets that orbit at the wrong angle, so there may be Earth-sized habitable zone worlds within 10 or 15 light-years of Earth right now. Worlds we cannot yet confirm because the geometry of space hides them from our instruments. That possibility is simultaneously one of the most exciting and most haunting ideas in modern science. Exciting because it means Earth twins may be common. Haunting because even a world 10 light-years away, with today's fastest spacecraft, sits nearly 200,000 years from reach. The universe filled itself with worlds, and then arranged them far enough apart that finding them is one achievement, and reaching them is an entirely different problem with no current solution. That gap between discovery and access, between knowledge and presence, may be the defining fact of humanity's position in the cosmos. And the question of whether anything on the other side of that gap knows we exist, or ever could, carries a weight that goes beyond science entirely. The distance to Trappist 1e is 239 trillion miles. That number has come up before in this story, but Chapter 18 is where it stops being an abstract fact and starts being a philosophical problem. Because the distance does not just prevent travel. It prevents communication. It prevents confirmation. It may prevent us from ever knowing, with certainty, whether the most Earth-like world we have ever found is alive or dead. Send a radio signal from Earth toward Trappist 1e right now, travelling at light speed, the fastest anything in the universe can move. That signal arrives in 40.7 years. If something on the other side receives it and responds immediately, the reply arrives back on Earth 40.7 years after that. The total round-trip time for a single exchange is 81 years. One message, one reply, 81 years. A scientist who sends that message at age 25 would be 106 years old when the reply arrived, assuming the reply came at all, and assuming anyone was still listening. This is confirmed physics, not a thought experiment. Confirmed. The speed of light is the speed limit of information in the universe. No signal, no matter how powerful, travels faster. This means that even if Trappist 1e is inhabited right now, and even if those inhabitants are actively broadcasting into space, the signal they are sending tonight will not reach Earth for another 40 years. And if they sent a signal 40 years ago, it is arriving somewhere in our solar system right now. Scientists have been scanning the sky for signals from other civilizations for decades, a field called the search for extraterrestrial intelligence. No confirmed signal from another civilization has ever been detected. Confirmed. Whether that means no one is broadcasting, our equipment is not sensitive enough, or the signals exist and we're simply not pointed in the right direction, is unknown. Unknown. The silence is one of the defining facts of our moment in history. We have found the most Earth-like world in our confirmed catalogue. We have pointed our best telescope at it. We got ambiguous results about its atmosphere, and no results at all about whether anything lives there. And the tools that could answer the question are still being built. Philosophers and scientists call the broader version of this problem the Fermi Paradox. The physicist Enrico Fermi once asked a question that has never been satisfyingly answered. Given the age of the universe, the number of stars and the apparent abundance of planets, where is everyone? If intelligent life exists elsewhere, the universe has had enough time for civilizations to expand, explore, and make themselves known, and yet the sky is quiet. Some argue the silence means intelligent life is extraordinarily rare. Others argue civilizations destroy themselves before they can broadcast across interstellar distances. Others suggest the universe is full of signals we simply do not know how to recognize yet. Trappist 1e sits at the center of all these questions, 40 light-years, close enough to study with the right tools, far enough that answers arrive in generations, not years. And the question underneath all of it, the one that gives the distance its real weight, is not just whether life exists there. The question is whether the universe will ever let us find out. Imagine standing on the surface of Trappist 1e. This requires some imagination, but every element of this picture comes from confirmed or well-supported scientific data. Confirmed and theory mixed. noted where appropriate. The ground beneath your feet is rocky and roughly Earth-textured. Gravity pulls at about 93% of what you feel on Earth, so you're slightly lighter. Your body feels almost normal. A quick jump sends you a little higher than expected. The sky above you is strange. You're standing in the Terminator zone, the thin ring between the permanent day side and the permanent night side. Behind you, the day side blazes. The star hangs enormous and unmoving on the horizon, filling far more of the sky than our star fills from Earth's surface. It appears red-orange, dim enough to look at without pain, but its ultraviolet output, invisible to the eye, has been bombarding this landscape for billions of years. Ahead of you, the sky darkens toward the night side. Stars appear in a sky that never fully brightens in that direction. The Terminator zone catches a perpetual low-angled light, like standing at the edge of a sunset that never ends and never moves. The temperature here might be survivable. Theory. Models suggest the Terminator zone could maintain liquid water conditions if an atmosphere circulates heat from the day side. Whether that atmosphere exists is still unknown. If you look up carefully at the right moment, you might see the other Trappist 1 planets crossing the sky. Because all 7 worlds orbit so tightly around the same small star, they would appear as visible disks moving across the heavens, much larger than planets look from Earth. On some nights, multiple worlds would be visible simultaneously, each one a reminder that this solar system is packed in a way ours is not. The star above you is about 10 times smaller in diameter than our own star. But because TRAPPIST-1e orbits so much closer to it than Earth orbits ours, the star appears larger in the sky than our own star does from Earth's surface. Confirmed, a bigger-looking star, dimmer overall, hanging motionless above the same horizon forever. You wait for sunrise, it never comes. You wait for sunset, it never happens either. Day and night are not events here, they are permanent hemispheres. The only cycle this world offers is the 6.1 Earth day orbit, one full loop around the star, which from the Terminator zone you would feel as a very slight shift in atmospheric pressure and temperature as different orbital geometry changes what the planet receives. A year here, by Earth definition, lasts about 60 of those 6-day orbits. 60 loops in roughly 365 days. The planet would have completed 60 full years around its star in the time Earth completes one. Biologically, a human standing on that surface would face immediate unknowns. The radiation environment without a confirmed magnetic field or ozone layer is potentially lethal on exposed surfaces. Unknown. Any shelter would need to be substantial. Any food system would need to be self-contained and shielded. The world is not friendly on its face, but it is built like ours, and it sits where liquid water could exist, and that combination has produced something extraordinary once before, on Earth. The question is whether the universe repeated the trick at 40 light years, and whether we will ever live long enough as a species to find out. Here is a number that almost never makes the headlines: 400 billion. That is the estimated number of stars in the Milky Way galaxy, not the observable universe, just our galaxy. One galaxy. 400 billion stars. Current estimates, built from Kepler's data and statistical modelling, suggest that roughly 1 in 3 of those stars hosts at least one rocky planet in a habitable zone. Theory, based on statistical modelling, 1 in 3. Run that math, and the result is somewhere around 130 billion potentially Earth-like worlds in our galaxy alone. 130 billion. If that estimate is anywhere close to accurate, the Milky Way is saturated with worlds where liquid water could pool on a rocky surface. Not confirmed, not verified, statistically inferred from the data collected so far. But the numbers are consistent and have held up across multiple independent research groups using different methods. And the Milky Way is one galaxy among an estimated 2 trillion galaxies in the observable universe. 2 trillion. If each galaxy holds even a fraction of the planets our own does, The total number of potentially habitable worlds in the observable universe exceeds any number that has a common name. So why does Earth feel alone? That is the core of what makes Trappist 1e and the entire exoplanet story feel so strange. The data says the universe is full of worlds. The silence says no one has called. The distance says even if we found the right world, getting there or hearing from it sits at the edge of physical possibility. Scientists use a term for this tension: the Great Silence. The universe appears built for planets. Life on Earth emerged relatively quickly after the planet cooled, suggesting it may not be an unlikely event given the right conditions. And yet, across decades of listening, no confirmed signal from another civilization has ever arrived. Several explanations exist. One is that life is common, but intelligent life is extraordinarily rare. Chemistry produces biology with some regularity, but the jump from single-celled organisms to tool-using, broadcasting civilizations may require a set of conditions so specific that it has happened almost nowhere else. Another explanation is that civilizations arise, reach a technological threshold, and then collapse before they can broadcast for long enough to be heard. Another suggests that advanced civilizations deliberately avoid broadcasting, staying quiet for reasons we cannot yet imagine. Theory, all of these. Trappist 1e holds a specific position in this debate. It is the most Earth-like confirmed world we have. It sits inside a habitable zone. It has passed initial tests for physical similarity with the highest confirmed score ever measured. And its atmosphere, the one variable that most directly determines whether life is possible there, remains an open question. If Trappist 1e has an atmosphere, contains liquid water, and has been geologically stable for billions of years, it had everything life needs for a very long time. Whether life used those ingredients is a question that current technology cannot answer, and the answer, if it exists, sits 40 light-years away, waiting for a telescope sensitive enough to read it. The next generation of instruments may be able to detect biosignatures, chemical signatures of biological activity, in the atmospheres of nearby exoplanets within the next few decades. Not confirmation of intelligence, confirmation of chemistry, oxygen, methane, ozone, in specific combinations that biology tends to produce, and geology alone tends not to. If those signatures appear in the spectrum of Trappist 1e, the implications for what the universe contains will be staggering, and if they do not appear, that silence carries its own kind of weight. The search for another Earth is also a search for a mirror. Every time scientists point a telescope at Trappist 1e or Proxima Centauri b, or any of the candidates in the catalogue, they are asking a version of the same question. Is what happened here repeatable? Did the combination of chemistry, energy, water, time, and stability that produced everything alive on Earth happen anywhere else? The question matters far beyond science. If life exists on Trappist 1e, then life is something the universe does regularly. It becomes a process, a likely outcome of planets in habitable zones, something that emerges wherever conditions allow. Life would be a feature of the cosmos, not an accident. If life does not exist on Trappist 1e despite its near-perfect similarity to Earth, the implications cut the other way. A world built almost identically to ours, sitting in the right zone, receiving the right energy, and still dead, would suggest that something about life is far rarer than the numbers imply, that the ingredients being present is not enough, that something else is required, something subtle, something we have not identified yet, and something Earth managed to provide. Both answers reshape our understanding of what Earth actually is. Right now, Earth is the only confirmed example of a planet that produced and sustained complex life. Every other data point in the catalogue is a candidate, a maybe, a world with the right address but an unknown interior. Trappist. 1e has the highest similarity score of any confirmed candidate, and its atmosphere, the variable that would most directly answer the habitability question, remains unmeasured with certainty as of right now. NASA's Pandora mission is aimed directly at this problem. Designed as a smaller, focused observatory, Pandora would monitor selected stars continuously, building detailed brightness maps that allow scientists to separate a star's own chemical noise from the signal of a planet's atmosphere. Applied to Trappist-1, it could give researchers the clean data needed to say with confidence whether Trappist-1e has a secondary atmosphere, what that atmosphere contains, and whether any of those chemicals appear in combinations that biology tends to produce. Confirmed mission, theory on results. Beyond Pandora, a proposed future mission called the Habitable Worlds Observatory would be specifically designed to directly image Earth-sized planets around Sun-like stars and analyse their atmospheres for biosignatures. It would target dozens of nearby systems and search for oxygen, water vapour, and methane in specific ratios that suggest active biology. No confirmed launch date exists yet, but the scientific community has identified it as a priority. Theory. The telescopes are getting better. The methods are improving. Scientists now know how to look in ways that were impossible 10 years ago. And Trappist-1e, sitting at 40 light-years, is close enough that the light carrying information about its atmosphere can actually be captured by instruments that fit within a spacecraft humans can build and launch. That is not nothing. In the scale of the universe, 40 light-years is a distance where the signal is still strong enough to be studied. The question is whether the next generation of instruments, pointed at the right moment with the right sensitivity, will find something in that signal that has never been found anywhere outside of Earth, and whether the species doing the searching will have the patience to wait for the answer across the timescales the universe demands. 40 light-years is the distance. But what does that distance mean for a civilization? Human history in its current form, cities, agriculture, writing, organised science, spans roughly 10,000 years. Modern scientific institutions, the kind capable of designing, building, launching and operating space telescopes, have existed for maybe 300 years. The scientific method as a formalised practice is even younger. The round-trip communication time to Trappist-1e is 81 years. One message, one reply, 3 or 4 human generations. Any real scientific dialogue across that gap would require an institutional patience that no human organisation has ever demonstrated at scale. Consider what 81 years meant in recent history. 81 years before this script was written, the Second World War was ending. The transistor had not been invented. DNA's structure had not been discovered. No satellite had ever been launched. The idea of a space telescope would have sounded like fiction. If scientists in 1945 had sent a signal toward Trappist-1e, it would be arriving there right now. If something replied immediately, the reply would reach Earth in 2106. Organisations that plan on 80-year return windows do not currently exist. Governments change, funding gets cut, priorities shift. The institutions of science operate on grant cycles of 3 to 5 years, not communication cycles measured in human generations. This is one of the least discussed but most fundamental barriers in the search for life beyond Earth. The physical distance is one problem. The civilizational patience required to act meaningfully across that distance is a separate, equally difficult problem. Some researchers argue that automated systems could handle the waiting. An artificial intelligence monitoring station, designed to listen for signals and respond automatically, could operate without human attention across decades. The reply, arriving 81 years later, would be processed by whatever version of that monitoring system existed at the time. Theory. Others argue that the communication problem is nearly irrelevant compared to the detection problem. The priority should be confirming whether Trappist-1e has an atmosphere, then whether that atmosphere contains biosignatures, then whether those biosignatures suggest complexity. None of those steps require communication with another world. They require only observation. An observation across 40 light-years is something current technology can begin to achieve. The honest picture of where humanity stands right now is this. We have confirmed the most Earth-like world known to science. We have pointed our most powerful telescope at it. We have gotten the first incomplete data on its atmosphere. We have proposals for follow-up missions. We have theoretical plans for sending probes to the nearest stars. Every one of those steps is real, and every one of them is also nowhere near enough to answer the question that sits underneath all of it. The question being, is there anyone there? And underneath that one, a quieter, stranger question that the distance forces into view. If there is, will we ever be able to say hello? The universe has a sense of scale that does not care about human urgency. 40 light-years sounds close on a cosmic map. On a map of the Milky Way, where the galaxy stretches 100,000 light-years across, and stars cluster in arms and clouds, 40 light-years is a tiny step. A fraction of the distance from one side of the galaxy to the other. But 40 light-years is also 239 trillion miles, 685,000 years at Voyager speed, and 81 years for a round-trip message. The universe did not design itself for creatures with 80-year lifespans and 300-year scientific institutions. The distances between stars were set by the physics of how galaxies form, by gravity and gas dynamics, and the initial conditions of the cosmos. No one arranged the stars with travel in mind. This creates a strange situation for a species like ours. We are intelligent enough to detect other worlds. We are precise enough to measure their sizes, temperatures, and densities from light years away. We are creative enough to propose missions and telescopes and probes with light sails, and we are physically, institutionally and technologically nowhere near capable of doing more than observing from a very great distance. The closest confirmed Earth-like planet is 40 light-years away. The best candidate is over 1,000 light-years away and unconfirmed. The closest exoplanet in any habitable zone is 4 light-years away and probably irradiated into sterility. The nearest exoplanet at all is less than 5 light-years away and boiling hot. The pattern holds at every scale. Every world worth examining sits beyond any reachable horizon. And yet something important happened in 2025 that shifts the story slightly forward. Not a breakthrough, not a confirmation, a narrowing. The James Webb Space Telescope ruled out one type of atmosphere for Trappist 1e. That ruling out matters. Science advances by elimination as much as by discovery. Knowing that Trappist 1e does not have a thick hydrogen-helium primary atmosphere tells scientists something real about the planet's history. A planet that lost its primordial atmosphere likely had enough geological or chemical activity to do so, which is itself a sign of a dynamic world. Dynamic worlds are more interesting to biologists than static ones. On Earth, the geological and chemical activity that drove early atmospheric change also drove the chemistry that preceded life. A world active enough to have shed its primary atmosphere and potentially built a secondary one is a world where things are happening. Whether those things include biology is still the open question, but elimination is progress. Narrowing is progress. Pointing the most powerful telescope ever built at the most Earth-like confirmed world ever found, and getting any data at all is progress, even if the data is incomplete. The next instrument that looks at Trappist 1e will know what the James Webb Space Telescope already ruled out. It will start from a narrower set of possibilities. Each generation of observation tightens the constraints. Eventually, the constraints will be tight enough that only one answer fits. Whether that answer arrives in 10 years, 50 years, or a century depends entirely on which missions get funded, built, and launched. And those decisions are made by humans operating on timescales that feel urgent to them, but are barely a blink in the history of the question being asked. The universe waits. The question waits. And the planet 40 light-years away keeps orbiting its dim red star, 6.1 days per loop, completely indifferent to whether anyone is watching. There is a version of this story that ends with hope. In this version, the Pandora mission launches successfully. It monitors Trappist 1 with the continuous attention the James Webb Space Telescope could not provide. Over months of data, scientists build a precise model of the star's chemical fingerprint, separating its noise cleanly from the signal, passing through Trappist 1E's edge during transits. The cleaned data reveals a secondary atmosphere, thin, maybe, but real, composed of carbon dioxide and nitrogen with trace amounts of other gases. A geological atmosphere, the kind a volcanically active world builds over billions of years. Then, in a follow-up observation using a more sensitive next-generation telescope, a faint signal appears in the spectrum that the models cannot explain with geology alone. The ratios of oxygen and methane in the atmosphere are too high to be produced by rocks and ultraviolet light. They match the ratios that biology produces on Earth, the footprint of organisms exhaling and metabolizing. The announcement would be the most significant scientific event in human history. Confirmed evidence of chemistry consistent with life on another world. The most Earth-like confirmed planet, 40 light-years away, carrying the chemical fingerprints of biological activity. That version of the story is possible. Every step in it is scientifically plausible. Theory. And there is another version. In this one, every subsequent telescope aimed at Trappist 1E finds nothing. The atmosphere, if it exists at all, is thin and geologically produced, carrying no signatures that biology alone explains. The Terminator Zone, the only potentially habitable strip on the planet, is swept by radiation from stellar flares that stripped the ozone layer long before complex chemistry could stabilize. The planet is quiet in every frequency scientists can measure. In this version, Trappist 1E is the most Earth-like confirmed world we will ever find at this range, and it is empty. A near-perfect physical copy of Earth, built by the same physics, sitting in the same kind of zone, producing nothing. Both versions are scientifically open right now. No evidence conclusively favours either one. Unknown. What makes this moment unusual in human history is that we are at the exact point where the instruments to begin answering the question exist, or are being built. This is the generation that first detected the atmospheres of other worlds, the generation that pointed the James Webb Space Telescope at Trappist 1E and got the first real data, the generation that proposed and funded follow-up missions. The answer may come in 20 years, it may come in 100. It may require a telescope not yet designed, launched on a mission not yet approved, operated by scientists not yet born. But the question is no longer purely philosophical, it is observational. It is scientific. It is being actively investigated with real instruments and real data, and 40 light-years, for all its crushing scale, is close enough that the light arriving from Trappist 1EN carries real information that real instruments can read. The universe arranged the distances, we arranged the telescopes, and somewhere in the overlap between those two facts, the answer to the biggest question in science is waiting. Every civilization that has ever looked up at the sky has asked some version of the same question. Are we alone? For most of human history, the question had no scientific framework. It was philosophy, religion, myth. The stars were lights in a fixed dome, gods, lanterns, mysteries without addresses. The idea that each point of light was a star like our own, potentially surrounded by worlds, was a fringe idea for most of recorded history. The shift began slowly. In 1600, a philosopher named Giordano Bruno argued publicly that the stars were distant suns with their own planets, and that the universe was infinite and full of worlds. The Church considered that view dangerous. Bruno was burned at the stake. 4 centuries later, the James Webb Space Telescope pointed at the most Earth-like confirmed world in the catalogue and measured what its atmosphere might contain. Bruno's intuition that worlds exist beyond counting has been confirmed more than 6,000 times over. The distance between those two moments, 400 years of science, is the distance between asking the question and being able to begin testing it. and the distance between where we are now and a confirmed answer about life on Trappist 1e may be comparable in scale. Science moves in generations. The exoplanet field itself is younger than most of the scientists who built it. The Kepler Space Telescope launched in 2009. The first confirmed exoplanet came in 1992. The James Webb Space Telescope launched at the end of 2021. Each instrument built on what the previous one found, each generation of scientists inheriting a narrower, sharper question from the one before. The scientists working on Trappist 1e's atmosphere today are working with data that did not exist 5 years ago. The scientists who will work on it 10 years from now will have data that does not exist today. Each new instrument adds resolution. Each new observation eliminates possibilities. This is how science actually closes gaps across decades, slowly, incrementally, with instruments that seem impossibly precise until the next one makes them look crude. And the gap between here and Trappist 1e is not just physical, it is informational. Each photon of light that arrives from that system carries a fragment of data about what the planet is doing right now, 40 years ago from its perspective. Enough fragments, gathered carefully enough, begin to form a picture. The picture is not complete. It may not be complete in any of our lifetimes, but the direction of travel is clear. Every decade, humanity's ability to read the light from other worlds improves. Every decade, the question of whether Trappist 1e is alive or silent gets a sharper scientific framework around it. The universe built the distance. Science is slowly, patiently building the tools to see across it. And the answer, when it comes, will land differently depending on which way it points. Because both outcomes, life confirmed and life absent, carry implications that reach far beyond the planet itself. If Trappist 1e is alive, the universe is teeming. That is the logical consequence of confirmation. Trappist 1e is not a rare, special case in an unusual corner of the galaxy. It is a planet orbiting one of the most common types of stars in the Milky Way, in a system with 6 other rocky worlds 40 light-years from Earth. If life emerged there, it almost certainly emerged in thousands of other habitable zone systems as well. The galaxy would be full of biology, spread across hundreds of billions of worlds, each one doing its own version of chemistry under a different star. That would mean Earth is typical. Life is a planetary habit. The universe generates it wherever the ingredients accumulate in the right arrangement. If Trappist 1e is silent, the implications cut differently. A world that scores 0.95 on the Earth Similarity Index, sits in a habitable zone, has a 6 billion year history, and still shows no signs of biology would suggest that life requires something beyond the basics. Something rare. Something Earth had that most other worlds do not. Scientists have proposed candidates for what that something might be. A large moon stabilizing Earth's axial tilt and preventing wild climate swings. Jupiter's gravity shielding the inner solar system from a continuous bombardment of comets and asteroids. The exact timing of Earth's magnetic field generation, plate tectonics, recycling carbon, and regulating long-term climate. A star that is unusually calm and stable. Theory, all of these. Each of these factors, and others, may have contributed to Earth's ability to sustain complex life for nearly 4 billion years. Remove any one of them, and Earth's history might look very different. Trappist 1a has some of these factors and lacks others. Of these, it orbits a stable, old red dwarf. It has roughly Earth-like gravity and density, but it lacks the comfortable orbital distance Earth enjoys. It may lack a stabilizing moon, it may lack a protective magnetic field, and its star, while quiet for a red dwarf, is magnetically more active than our own. The comparison is never clean. No other world in the catalogue is Earth. Every candidate resembles Earth in some ways and diverges in others. The divergences may matter enormously for life, or they may matter not at all. The only way to know is to look closely enough, and the tools to look closely enough are being built and pointed right now, in real time, by real scientists working on the most important question ever asked by any species on any planet that we're aware of. Whether anyone on the other end of 40 light years is asking the same question back remains the deepest unknown in science, and the answer, in either direction, will define what kind of universe we actually live in. The search does not end at Trappist 1e. Scientists are looking at dozens of nearby systems simultaneously. Telescopes scan for atmospheres, for chemical signatures, for any deviation from what dead rock chemistry produces. The catalogue grows every year. New systems get added. Old candidates get refined or eliminated. The picture of the local cosmic neighbourhood sharpens slowly. Within 100 light-years of Earth, the James Webb Space Telescope can study the atmospheres of rocky planets around small stars with meaningful sensitivity. That sphere of 100 light-years contains thousands of stars. Statistical estimates suggest dozens of potentially habitable worlds sit inside that range. Theory. The problem again is geometry. A planet only shows its atmosphere to our telescopes when it passes in front of its star from our line of sight. Most planets, even Earth-like ones, orbit at angles that never produce a transit visible from Earth. For every system we can study using transit methods, several more exist at angles we cannot see. Future space telescopes designed to image planets directly, rather than waiting for transits, could in theory examine a much larger fraction of nearby stars. These chronograph telescopes block out the light of the star itself, like holding your thumb up to block the sun, and photograph the faint planets beside it. At visible and infrared wavelengths, a planet's reflected light and thermal glow can carry atmospheric signatures. The proposed Habitable Worlds Observatory would operate this way, directly imaging Earth-like planets around Sun-like stars within about 40 to 60 light-years, and analysing their spectra for biosignatures. If funded and built in the coming decades, it could examine dozens of candidates. Theory. Each of those candidates carries the same weight as Trappist 1e. Each one is a place where biology either happened or did not. Each one is a data point in the most important statistical question in science. What fraction of potentially habitable worlds are actually inhabited? If that fraction is high, the galaxy is alive. If it is low, Earth is nearly alone. And the answer to that fraction, extrapolated across 400 billion stars in the Milky Way and 2 trillion galaxies beyond it, gives a number that defines the nature of reality more completely than almost any other fact we could discover. The number of inhabited worlds in the observable universe. How many places have looked up at the sky and wondered? How many places have built telescopes, or something like telescopes, and pointed them at their neighbours? Trappist 1e is one candidate for that number. One world 40 light-years away, silent so far, atmospherically ambiguous, physically Earth-like, sitting in a habitable zone around a quiet red star. It may be empty, it may be full of something extraordinary, or it may be inhabited by something so simple, single-celled organisms in a coastal ocean somewhere in the Terminator zone, that confirming it requires instruments we have not yet designed. The universe does not rush this answer. It holds it across 40 light-years of silence and waits. And the species doing the asking has been at it, in the modern sense, for about 30 years. 30 years. Against a question that has been waiting 4 billion years for someone to ask it clearly enough to deserve an answer. Here is what we actually know, stripped of all uncertainty. Trappist. 1e is real. Its measurements are confirmed by multiple telescopes and multiple methods. Confirmed. Its radius is roughly 91% of Earth's. Its mass is roughly 77% of Earth's. Its density is close to identical to Earth's. Its gravity at the surface is about 93% of what you feel standing here. It orbits inside its star's confirmed habitable zone. Its orbital period is 6.1 Earth days. It is tidally locked to its star. Its distance from Earth is 40.7 light-years, equal to approximately 239 trillion miles. Confirmed. At Voyager 1 speed, reaching it takes 685,000 years. At 20% light speed using proposed breakthrough starshot technology, reaching it takes roughly 200 to 270 years. At light speed itself, it takes 40.7 years each direction. Confirmed and theory noted respectively. The James Webb Space Telescope observed it in September 2025 across 4 transits. It ruled out a thick primary hydrogen-helium atmosphere. The remaining atmospheric data is ambiguous. A possible methane signal was detected and is most likely stellar contamination rather than a planetary signature. Confirmed ruling out theory on methane interpretation. Beyond those facts, every other statement about Trappist 1e carries some level of uncertainty. Whether it has a secondary atmosphere is unknown, whether it has a magnetic field is unknown, whether liquid water exists on its surface is unknown, whether anything alive has ever touched its ground is unknown. Unknown, all of these. Those unknowns are not failures of science, they are the current frontier. Each unknown represents a measurement waiting to be made by an instrument capable of making it. The confirmed facts about Trappist 1e already represent an extraordinary achievement. A generation ago, no one knew this planet existed. A decade ago, its physical properties were rough estimates. Today, scientists know its density to within a few percent, have observed its atmosphere with the most powerful space telescope ever built, and are planning follow-up missions specifically designed to push the remaining unknowns toward answers. Science does not close all unknowns simultaneously. It closes them one instrument at a time, one observation at a time, one generation of scientists handing the next generation a narrower question. The question about Trappist 1e has been narrowed. A primary atmosphere has been ruled out. The next narrowing will come when Pandora's data separates stellar noise from planetary signal. The narrowing after that will come when a more sensitive telescope examines specific chemical ratios in whatever atmosphere remains. Eventually the question narrows enough that an answer appears. That answer may be definitive and clear, or it may be deeply ambiguous and require yet another instrument. Science rarely delivers clean moments. It delivers a slowly sharpening picture. The picture of Trappist 1e is sharpening right now, and every person alive today is watching the sharpest images of the most Earth-like confirmed world ever found come into focus in real time. That is an extraordinary moment to be standing in, even from 239 trillion miles away. The distance to Trappist 1e matters not just because it is large, it matters because of what it reveals about the structure of the universe at the scale where intelligent life operates. Stars form in clusters and drift apart over billions of years. Our own star is in a relatively sparse region of the Milky Way, between 2 spiral arms, without the dense stellar crowding of the galactic core. The nearest individual star, Proxima Centauri, sits 4.22 light-years away. The nearest star system with multiple stars, Alpha Centauri, sits 4.37 light-years away. The average distance between stars in our region of the galaxy is several light-years. Several light-years, at the speeds humanity can currently achieve, means hundreds of thousands to millions of years of travel. At any speed below a significant fraction of light speed, interstellar distances are functionally permanent barriers. This is almost certainly not an accident of our particular neighbourhood. It is the general condition of the galaxy. Stars are spread out. The gaps between them are vast by any biological or technological measure. A civilization on any rocky planet in any habitable zone anywhere in the Milky Way faces essentially the same problem we do. The nearest interesting neighbour is years of light travel away. If interstellar travel ever becomes achievable for any civilization in the galaxy, the travel timescales involved suggest that civilizations would have to plan across centuries to millennia just for one-way journeys to nearby systems. A civilization capable of that kind of planning would need social, political, and institutional structures of a kind human society has never sustained. Some scientists argue that this universal barrier is the answer to the Fermi Paradox. The distances are simply too large, and the timescales too long for civilizations to physically spread through the galaxy in a way that makes them detectable. Even an ancient civilization, millions of years old, might never have made it further than a handful of star systems from its home. Theory. Others argue that sufficiently advanced propulsion, forms of travel we cannot currently imagine, would eventually overcome the distance. They point out that chemistry, the basis of all known life and all current propulsion, has physical limits, but physics allows for energy densities and propulsion mechanisms that biology has not yet discovered. Theory. Both arguments are currently theoretical. What is confirmed is that the universe does not appear to have been designed for ease of travel. The distances are what they are, the speed limit is what it is, and every civilization that has ever existed, if any others have, faced the same arithmetic we face now. Trappist 1 sits at 40 light years. That is the number at the centre of this entire story. Every fact about the planet, every theory about its atmosphere, every proposal for sending probes or messages or signals runs into that number eventually. 239 trillion miles of empty space, 40 years of light travel time one direction, and on the other side of it, a world built almost exactly like ours, orbiting its star once every 6 days, waiting for someone to figure out whether it matters. The people working on this problem right now are real. They're astronomers at universities, instrument engineers at space agencies, theorists writing models of planetary atmospheres, mission planners calculating launch windows and orbital mechanics. They work in ordinary offices and observatories. They write papers and argue at conferences and reanalyze data late at night when a signal looks different than expected. The question they are working on is the oldest question humanity has ever asked with scientific tools. Is Earth the only inhabited world? After the James Webb Space Telescope's TRAPPIST-1e observations in September 2025, the researchers who analysed the 4 transits split into cautious camps. Some were encouraged by traces in the data. Others were firm that the signal could not be separated cleanly from stellar noise. The disagreement was honest and scientific, exactly the kind of productive tension that drives fields forward. The team behind the Pandora mission, designed to provide the continuous stellar monitoring needed to clean up that ambiguity, has been building their instrument with this specific problem in mind. Pandora would watch selected stars for long stretches, mapping the star's behaviour in enough detail that when a transit occurs, the planetary signal can be isolated from the star's own chemical fluctuations. Applied to TRAPPIST-1 and TRAPPIST-1e, it could give researchers their first genuinely clean atmospheric data. Beyond Pandora, the broader scientific community has flagged the Habitable Worlds Observatory as a priority. This proposed flagship telescope would directly image Earth-sized planets around nearby sun-like stars and analyse their light for biosignatures. A planet does not need to transit its star for this method to work, which would open up a far larger sample of nearby systems to study. Each of these missions represents years of work by hundreds of scientists, funded by governments, justified to policymakers, and built by engineers solving problems no one has solved before. The timeline from proposal to launch to results typically spans a decade or more. The answer to whether TRAPPIST-1e has life may require several generations of this work. It may require a telescope that does not yet exist, operated by scientists not yet in graduate school, funded by a mission not yet approved. Or it may require only what Pandora can provide. If the data comes back clean, and the atmosphere contains the right combination of gases, the announcement could come faster than anyone currently expects. Science has surprised itself before. Discoveries have arrived ahead of schedule when the right instrument looked in the right place at the right moment. TRAPPIST-1e is in the right place. The right instruments are being aimed at it. The right moment is not known yet, but it is coming. And the people working toward it have chosen to spend their careers on the most important question any member of any species has ever spent a career on. That choice, made by ordinary people in ordinary buildings with extraordinary instruments, is how the distance to Trappist 1e will eventually mean something other than impossibility. The light from Trappist 1e is arriving right now. Every second, photons that left that system 40.7 years ago are streaming into our solar system, bouncing off mirrors, hitting detectors, and carrying information about a world built almost exactly like ours. The James Webb Space Telescope catches some of them. Ground-based observatories catch others. Future instruments will catch more of them, more precisely, with better ability to decode what they carry. Light does not care about the distance it travelled to arrive. It carries its information regardless. A photon that passed through the edge of Trappist 1e's atmosphere, absorbing a specific wavelength that methane or oxygen or water vapour removes from its spectrum, carries that chemical fingerprint across 40 light years and delivers it intact to any instrument sensitive enough to read it. This is the mechanic that makes atmospheric science of distant worlds possible at all. The distance is enormous, the signal is faint, but the information is real, embedded in the light, preserved across the journey. Every improvement in telescope sensitivity and detector precision extracts more of that information from the same arriving photons. 30 years ago, scientists could confirm that stars had planets by watching them wobble. 20 years ago, they could measure some planetary sizes and orbital periods. 10 years ago, they could detect the bulk compositions of large exoplanet atmospheres. Today, they are attempting to read the chemical fingerprints of rocky, Earth-sized atmospheres 40 light-years away, with an instrument that was considered technically impossible to build when the first exoplanet was confirmed. 10 years from now, the instruments will be more sensitive again. 20 years from now, more sensitive still. The trajectory of improvement in this field has been steep and consistent. Each new telescope generation does not just look further, it reads the same nearby objects more deeply. Trappist 1e will be studied by every major telescope humanity builds for decades to come, because it holds the answer to a question that does not go away. And every time a new instrument points at it, the data gets a little richer, the picture gets a little sharper. The range of possible answers narrows a little more. The universe is 40 light-years wide at this particular crossing. The photons carrying the answer are already in transit. Some of them left Trappist 1e before this script was written. Some of them will arrive after everyone listening to it has died. But they carry the same information either way. The universe does not edit its records based on who is watching. The question is only whether the instrument waiting on this end is good enough to read what the light has been carrying for 40 years. And getting that instrument right, building it, launching it, pointing it correctly, and having the patience to wait for the data is the entire project of the next chapter of human science. There are two ways this story ends. In the first ending, humanity eventually reads the light from Trappist 1 clearly enough to find what biology leaves behind. The chemical signature of life, the combination of gases that geology alone cannot produce, appears in the spectrum. The confirmation takes years of analysis and independent verification. It survives every challenge scientists throw at it. The conclusion stands. Earth is not the only inhabited world. Life happened twice, at minimum, in this galaxy. The universe generates biology wherever the conditions appear. The Milky Way, with its 130 billion potentially habitable worlds, is alive in ways we never confirmed before. The question of whether we are alone resolves permanently with the answer no. The distance remains 239 trillion miles. We still cannot get there. We still cannot communicate meaningfully across 81-year round-trip delays. But we know. In the second ending, every telescope pointed at Trappist 1e finds nothing. No atmosphere or a thin, bare geological one. No biosignatures. No chemical fingerprints that require living organisms to explain. The planet scores 0.95 on similarity to Earth, sits in a habitable zone, has been there for billions of years and carries no sign of anything alive. The most Earth-like confirmed world in the catalogue is empty. That ending does not prove life is absent everywhere. It proves only that one specific world, with one specific history, around one specific star, did not produce confirmed biology. But the weight of that finding would shift the scientific conversation dramatically. The question of what makes Earth different would move from philosophy to urgent investigation. What ingredient did Earth have? What protected it that Trappist 1a lacked? Both endings change everything we think we understand about life and its place in the universe. Right now, neither ending has arrived. The data is ambiguous, the instruments are improving, and the planet continues its 6.1-day orbit completely indifferent to the attention. 40 light-years away, 239 trillion miles, a world built like ours, waiting, and humanity, standing on the only confirmed inhabited planet in the universe, pointing its best tools at the night sky, is getting closer to finding out. Here is the question underneath every question in this story. If another world like ours exists, if it has oceans and air and something living in it, separated from us by 40 light-years or 400 or 4,000, does the distance mean we are alone? Distance and solitude are not the same thing. A family spread across a continent is still a family. Two cities separated by 1,000 miles are still cities, still full of people, still part of the same civilization even if they never meet. If Trappist 1e is alive, and we confirm it, and we can never reach it and cannot meaningfully communicate with it, we are alone in the practical sense. We will never share anything with whatever lives there. We will never exchange knowledge, or art, or warning. The gap is too large and the speed limit too strict. But we will know, and knowing changes the interior of the question completely. Knowing that life exists elsewhere means life is not a singular accident. It means the universe is, in some sense, trying. That under the right conditions, chemistry organises itself into something that looks back at the sky. That the 40 light-years between us and Trappist 1a is a gap between two places that share at minimum the property of being inhabited. That knowledge changes what Earth means. It changes what life means. It changes the answer to the question Bruno asked 400 years ago, when he looked up and guessed that the stars were not lonely lights, but suns with their own worlds beneath them. And if the answer goes the other way, if every telescope confirms that Trappist 1e is empty, and the next candidate is empty, and the galaxy turns out to be full of worlds that almost supported life but did not quite manage it, that answer matters too. It means Earth is something the universe struggled to produce, something that required an improbable chain of conditions held together across 4 billion years to generate complexity and intelligence and the ability to ask what is out there. That would make Earth rarer than anything we currently know, and it would place on the species living here a weight and a responsibility that nothing else in the cosmos appears able to carry. Either way, the distance to Trappist 1e is the distance to the answer. 239 trillion miles of space carrying information in light, arriving a little at a time, being read by instruments getting better every decade, aimed by scientists spending their careers on the oldest question anyone has ever asked. The planet is there. The light is arriving. The instruments are pointed, and in some year that no one alive today can name with certainty, the picture will be sharp enough. When it is, humanity will know whether it has company in the universe, whether the long silence of the sky means the universe is empty around us, or only that the distances between living worlds are simply too large for voices to carry. The answer is 40 light-years away, and we are already looking.